So welcome back, and today we want to look at a non-parametric equivalent to the one-way ANOVA. So here we have a data set, another fictitious data set, and we have two variables. We have type of deadlift, and we have hamstring soreness rate in 48 hours post deadlift. And if you don't know what a deadlift is, you could Google it. It's just an exercise that's done that helps to strengthen the hamstring and other muscles. So we're basically comparing to see want to compare to see what the different types of deadlifts. So if you look here, go to our value labels. So you have the conventional deadlift, the Romanian deadlift, and the sumo deadlift. So we want to compare to see these three different types of deadlifts in our sample of persons to see, you know, if one of the deadlifts, if at least one of the deadlifts created significantly higher soreness, or the rating of soreness in the athletes or the persons who would have done the deadlift. We could have done a one-way ANOVA, but say for example, for some reason, the requirements of the one-way ANOVA weren't met. For example, the samples were not normally distributed, the sample sizes were small, so the variances, we couldn't assume equal variances. So what we could do in replacement of that, we could do a Kruskal-Wallis H-test, which is a non-parametric equivalent to a one-way ANOVA. But this also has some requirements, and let's look at that. So the requirements for the Kruskal-Wallis H-test is that we have to have at least 3 independent samples, yes, which makes sense and we should know. There should be at least 5 observations in each sample. You know, this might be somewhat of a loose requirement, but because the H statistic, its distribution is approximated to a chi-square distribution, and chi-square also has similar requirements as this. But, you know, for the tests and the p-value you get to be credible or to be trustworthy, you know, that you could make good assumptions from it or good inferences from it, is that you need at least 5 observations, and as we know, the sample should be random samples. So let's get back to our data set. So here in our data set, we could just go in data view. So you see the different types of deadlift and the hamstring soreness rating values. So we want to see if the average value was the same for each type of deadlift. And because we're doing a non-parametric, we're not looking at means, we'll practically be looking at medians. Right, so let's do this test. So we'll go to analyze, we'll go to non-parametric, and we'll go to K independent samples, right? Because we're looking at many independent samples. So we want to put the hamstring soreness in the test variable, and then for the type of deadlift, we're going to put it as our grouping variable. All right, let's define the groups. So for the lower limit would be conventional, which was assigned 0. And then for the upper limit, we'll put sumo, which was assigned 2. Right? Because we want to ensure that it compares all 3. So you put the lowest number and the highest number. We click continue. And we want to do the Kruskal-Wallis H-test. So ensure you check that. And then you press OK. And here we get our output. So in our output, what we see here is mean rank. And before we interpret this, we just want to come here to look. So we get a chi-square value, which would be approximated to the H statistic. And we'll look at here at our p-value. The p-value is 0.001, which is less than the conventional alpha of 0.05. So which tells us that we could reject the null hypothesis. And the null hypothesis in this scenario would be that the median soreness rating for all 3 types of deadlifts would be equal or would be the same. But because we reject the null hypothesis, we are then saying that there is evidence to indicate that at least one of them has a mean that's different from the others. And if we look at them here, all of them, they seem pretty different. And one thing I want you guys to know is that in PSPP, when doing the Kruskal-Wallis test, we don't have an option for multiple comparison tests. Okay, but there are other ways we could informal ways we could use PSPP to look at this. But there are tests that could be done, but PSPP does not have those tests, right? So if you look at the mean rank, we could see that Sumo had the lowest mean rank compared to Romanian, which are the highest. And this gap seems pretty wide, and it could tell us that, you know, the difference between those two might be significant. There's a good difference in mean rank between conventional and Romanian as well. But when you look at the gap between Sumo and Romanian, it's a little bit wider than the others. What we could do as well, we could probably do a box plot as an informal means of comparing the different medians. So we'll go back to our data set. And here we click Analyze, we go to Descriptives, we go to Explore. So we put our hamstring rating, soreness rating into the dependent list, and in the factor list we put the type of deadlift. We'll just indicate plots, and in plots we want to ensure that we have box plots and we have factor levels together. We could uncheck histogram, we click Continue, and then we could click OK. And then we come back to our output view. And in our output view, we're looking at this. You could see that there's still some amount of overlap. There's still some amount of overlap when you look at the middle 50% of the values in each sample. But you see the overlap for conventional and Romanian is actually greater, and the median are actually very close. But if we look at the median for Sumo compared to Romanian deadlift, the difference is a little bit more marked compared to the difference between conventional and Sumo. So this is just an informal way, or you could, you know, look at this and you could make some assumptions or inference from the data. And that is how you perform the Kruskal Wallis test using PSPP.